I'll explain what is meant by curvature of a curve. The curvature of a curve measures how sharply a curve bends. In the following figure, a bend at point P is more sharp than the bend at point Q. Now the question arises how to measure the amount of bend in a curve. So here the bend is more than the bend here, but the question is how to measure this bend. To answer this question, we need to define certain terms. First term is what is parameterization. A continuously differentiable map alpha AB to R2 is called parameterization of the curve alpha t. So alpha t is image. Image is a curve and the map is parameterization. Examples of parameterizations are alpha t equal to t, comma 2t plus 3 is a parameterization of line. Alpha t equal to t, comma t square is parameterization of a parabola. Alpha t equal to cos 2t sin 2t is a parameterization of a unit circle. So next is unit speed parameterization. Notice that the vector alpha dot t is derivative of this parameterization. So the derivative vector, so this is derivative vector. So derivative vector is tangent to the curve alpha t. And if length of this tangent is always 1, then the map is called a unit speed parameterization. Examples are, consider this psi s equal to sin s comma cos s. This is a unit speed parameterization of a circle. But here alpha t equal to cos 2t sin 2t, this is also a parameterization of a circle, but this is not a unit speed parameterization. So take its derivative. Alpha dot t is minus 2 sin 2t 2 cos 2t. If you find its norm, that will come out to be root 2, and here the norm is 1. So this is a unit speed parameterization of the same circle whose one parameterization is this. Next is regular parameterization. A parameterization is regular if this alpha dot t, that is the tangent vector, is not 0 at any point. So from here onward, we shall assume that every curve is a regular curve. That is, the tangent at every point of the curve is non-zero. So the students are advised to see why this condition has been imposed. Next is reparameterization. Now, if phi CD to AB is a bijective map such that both phi and phi inverse are differentiable, so phi is map such that phi and phi inverse are differentiable, and this phi alpha is a parameterization, then the composition alpha of phi. So this composition will be called reparameterization of the curve alpha. So example of a reparameterization is this psi s cos s comma sin s is a reparameterization of the map alpha t cos 2t sin 2t. So these both parameterizations are of unit circle. So we'll see that one is parameterization of another. So define this map phi as phi s equal to s by 2 and compute alpha of phi s, which is equal to alpha s by 2, because I have taken phi s as s by 2, and alpha is defined as cos 2t sin 2t. So this is cos 2s by 2 sin 2s by 2. We get cos s sin s, which is the psi s. So alpha of phi is psi. So it means psi is reparameterization of the map alpha. Next theorem is every curve alpha can be reparameterized into a unit speed parameterized. So I'll not give proof of this theorem, but it is very important that if you have any parameterization, we can find a new parameterization of the same curve, which is the unit speed parameterization. But I must tell you, it is not always easy to find a unit speed parameterization, but the theorem says the unit speed parameterization always exists. So next is arc length parameterization. A curve alpha AB to R2 is said to be parameterized by its arc length if for each S belong to AB, the length of the curve from alpha A to alpha S is S minus A unit. What it means? So this alpha is a parameterization of this arc. So I say this alpha is arc length parameterization if image of this length is exactly equal to the length itself. So here the length is s minus a units. The image curve must have length s minus a units. If these two things are equal, then we say the curve is arc length parameterized. For example, this map alpha 0 to pi to R2 defined by alpha t equal to cos 2t sin 2t. This map is not arc length parameterized because here the image 0 to 2 pi covers the whole circle. The length of whole circle is 2 pi. So, but here the length of interval is pi. So, length of, of pi unit covers a length of 2 pi units. So, length of domain is not same as the length of range. So, that's why this example is not of a curve which is arc length parameterization. So a curve alpha is arc length parameterization if and only if it is a unit speed parameterization. This theorem gives me a relation between arc length parameterization and a unit speed parameterization. So theorem says that two parameterizations are same. If one says that I have unit speed parameterization, it means that parameterization is arc length parameterization. And if we say I have arc length parameterization, it means I have a unit speed parameterization. So I skip this example for the moment due to shortage of time. In this example, I have shown that if you have some parameterization, we can find its arc length parameterization. So next, now I can define how to compute a curvature. So alpha, suppose a given unit speed curve. So unit speed curve means its tangent has length 1. So tangent norm of ts equal to 1 means ts vector dot ts vector is equal to 1. So take derivative with respect to s. We get first derivative of second plus second to derivative first equal to 0. So that will give me this t dot with dot product ts equal to 0. So this means, so this is my tangent vector t and this is derivative vector. So this relation t dot with dot product t is 0 means these two vectors are orthogonal. And suppose in this direction, this n is a unit normal vector. So it means this vector t dot is a multiple of the unit normal vector. So t dot s is equal to k times this unit normal vector. So this k is called curvature of the curve at this point S. So this curvature I have defined only for a unit speed curve. So this formula is not valid for any curve. Suppose we have given some curve which is not a unit speed curve. We need to first convert into a unit speed curve and then take its tangent vector and then take derivative of the tangent vector and then take norm of the derivative of the tangent vector. That norm will give you kappa s, which is called curvature at the point s.